that is concept of resonance. With respect to chapter 2, the previous gate questions I will solve after completing this resonance concept and coupled circuits concept. Combined, I will solve the questions. Okay. In the previous sessions that I discussed about in AC analysis, what are the observations from fundamentals of AC analysis? And if the sinusoidal AC source is applied to the resistive element, inductive element, capacitive element, what are the observations? If it is applied to RL, RC, RLC, series circuit and parallel circuits, what are the observations? All this I already explained. Even resonance concept also one of the AC analysis concept. Even coupled circuits also AC analysis. In AC analysis, one more topic that I am starting, the concept of resonance. With respect to resonance, mainly these are the concepts that I would like to discuss. First, I will start with some introduction. Types of resonance. Applications of resonance effect. And resonance in series circuits. Mainly two concepts, resonance in series circuits and resonance in parallel circuits. With respect to resonance in series circuits, these are the subtopics. That is variation of current, impedance, reactance, resistance with respect to frequency. That observations are important. With respect to frequency, how the current, impedance, reactance, resistance is varying. Frequencies at which voltage across the inductor and capacitor is maximum. That is what frequency in resonance circuit, at what frequency voltage across the inductor is maximum, voltage across the capacitor is maximum. All these concepts with respect to series resonance. That is resonance in series circuit. Then concept of quality factor, bandwidth and cutoff frequencies, power factor at cutoff frequencies. What is the power factor at cutoff frequencies? Relationship between bandwidth and quality factor, selectivity concept, relationship between bandwidth, selectivity and quality factor, then relation between quality factor and the damping ratio. All these with respect to resonance in series circuit. Then after completing resonance in series circuit, we have to see some practice questions with respect to this concept. Practice questions. Then after completing this, then resonance in parallel circuits, same concept. Variation of current, admittance, acceptance, voltage and phase angle with respect to frequency, quality factor, bandwidth and cutoff frequencies, selectivity and relationship between bandwidth, selectivity and quality factor, relation between quality factor and damping ratio, practical parallel resonance circuit, that is the tank circuit concept, then dynamic impedance, then finally practice questions. Yeah, these are the concepts that I would like to discuss with respect to resonance loops. Then first, we'll start with some introduction, then types of resonance, application of resonance effect, then finally I will start the resonance in series circuits. We'll see some introduction points. All of you well know this. Resonance is the frequency response of a circuit or network. That is, resonance is studied for what the frequency response of a circuit or network when it is operating at its natural frequency. If it is operating at a natural frequency, not excitation frequency, when it is operating at natural frequency, what is the response of a circuit? That is called resonance. That is the resonance frequency. Resonance occurs whenever natural frequency of oscillation of system coincide with the frequency of driving force source in electrical circuit. That is, there is a frequency of oscillations. For example, if you take the voltage across the inductor or voltage across the capacitor, or you have to take what the response of RLC circuit with AC excitation, whatever the response we are getting, there is some oscillations we can get at output side. There is some oscillating frequency. If that oscillating frequency equal to driving frequency, that is excitation frequency, then we can say that it is at resonance condition. That is, resonance occurs whenever natural frequency of oscillation of a system, this is a system oscillating frequency, is equal to driving force, that is the source frequency. Resonance in an electrical circuit because of presence of storage elements, very important. The main reason for existence of the resonance is because of storage elements in a circuit. What are the storage elements? That is inductor and capacitor. We know that inductor is having the energy in the form of magnetic field and capacitor is having energy in the form of electric field. And resonance in electrical circuit is because of the storage element. Which are the storage element that I told? Inductor and capacitor, which stores the energy in the form of magnetic field, which store the energy in the form of electric field. Clear? All these are the introduction points that you have to consider. At a fixed frequency, L and C elements will exchange energy freely as a function of time. We know that There is a transfer of energy from inductor to capacitor or capacitor to inductor. Because of this transfer of energy from inductor to capacitor or capacitor to inductor, there is a sinusoidal oscillations. There is a sinusoidal oscillations either across inductor or capacitor. Just a minute. Sorry, yes. That is at a fixed frequency, L and C elements will exchange energy freely as a function of time. During this exchange of energy from inductor to capacitor or capacitor to inductor, during exchange of energy from inductor to capacitor or capacitor to inductor, there exists a sinusoidal oscillations across the inductor or capacitor. These sinusoidal oscillations are having some frequency. The sinusoidal oscillations are having some frequency. This oscillations frequency is equal to system excitation frequency. Then we can say that it is under resonance condition. That is the meaning. Resonant frequency indicates that rate at which energy transformation is done between inductor and capacitor. At what rate the energy is transferring between inductor and capacitor, that is given by resonating frequency. Under resonance condition, the total supply voltage and supply current in phase. The reason also I will explain. Under resonance condition, the supply voltage and supply current is in phase. That is V and I is in phase. That is at resonance condition. That is at resonance condition. V and I is in phase means the circuit is purely resistive. Under resonance condition, the circuit is purely resistive. The circuit is purely resistive, and if it is a purely resistive, it is operating at unity power factor. The proof also I will give, but these are the general important points, introduction points that you have to consider. This is at resonance conditions. That is at resonance condition, voltage and currents are in phase, the circuit is purely resistive, and it is operating at a unity power factor. And maximum power is transferred to the entire circuit by the source. Under this condition only, a maximum power is transferred to the entire circuit. Next, what are the types of resonance? The resonance circuits are, that is based on the circuits. Types of resonance means series resonance, parallel resonance. Series resonance means that is not the meaning of type of resonance. That is the resonance in the series circuits. If resonance is in the series circuit, that is called series resonance. We don't have any series resonance. That is a resonance in series circuit. That is the meaning. Parallel resonance means that is the resonance in the parallel circuits. Generally, in series circuits, we have to take the series RLC circuit. How to take the series RLC circuit. Series RLC circuit. Then that is nothing but if you analyze the resonance in series RLC circuit, then it is called series resonance. And we have to see the parallel resonance. Parallel resonance means that is the resonance in parallel RLC circuit. That is the resonance in parallel RLC circuits. That is R and L. You have to take C. Okay. This type of circuit is nothing but a parallel RLC circuit. That you will see resonance in the parallel RLC circuit, then it is called parallel resonance. Yes, first we will start with before starting the resonance in series circuits, what are the applications of resonance effect? Where we can use this resonance applications. Most common application is tuning circuits. One of the main applications of the resonance is the tuning circuits. For example, when you tune a radio to a particular station, you are tuning the radio to radio station for a particular station, for a particular frequency we are tuning. The LC circuits are set at resonance for that particular carrier frequency. Then we can, that is, we can match that frequency. Yeah, that is nothing but a tuning circuits. The LC circuits are set at resonance for that particular frequency. Then we can match that frequency. That is, in tuning circuits, you have to use the resonance condition. That is the resonance effect. A series resonance circuit provides voltage magnification. Later on, give the proof also. By using a series resonance, that is, series resonance circuit acts as a voltage magnification circuit. Parallel resonance circuit acts as a current magnification circuit. How it is a voltage magnification, how it is a current magnification, later on that we'll see. A parallel resonance circuit can be used as load impedance in output circuit of radio frequency amplifiers. Due to high impedance, the gain of amplifier is maximum at a resonance circuit. That is, in radio frequency amplifiers, we have to use the parallel resonance circuit as a load impedance. Once it is used as a load impedance circuit, due to high impedance, the gain of amplifier is maximum. You know that at parallel resonance condition, in parallel circuit, at resonance condition, impedance is maximum. I'm not talking about series. In a series circuit, at resonance, impedance is minimum. But in parallel circuit, at resonance, impedance is maximum. If impedance is maximum at output side, output is also maximum, gain is maximum. For that purpose, we are using parallel resonance circuit is a load at output of the RF amplifiers. Both parallel and series resonance circuits are used in induction heating application. In induction heating applications also, we have to use this parallel resonance circuits. Yeah, these are the applications of resonance circuits. Now we'll see, first I'm starting resonance in series circuits. What the concept of resonance in series circuits? Let's consider a series RLC circuit. Let's consider a series RLC circuit as shown in figure. That the supply voltage, the RMS value of supply voltage is V, and take the voltage across the resistor is VR. Voltage across the resistor is VR. Voltage across the resistor is VR. And take the voltage across the inductor is VL. Voltage across the inductor is VL. Let the voltage across the capacitor is VC. This is VC. And this is the supply voltage. And this is the supply voltage. At a frequency F. The frequency of supply voltage is F. That is the excitation frequency is F. That is the supply frequency. Let's consider series RLC circuit. How to write the impedance of the circuit? Let's consider series RLC circuit. Let's consider series RLC circuit. Series RLC circuit. If you consider the series RLC circuit, then what is the impedance of the circuit? The impedance of the circuit. The impedance of the circuit. Z equal to ZR plus ZL plus ZC. Z equal to ZR plus ZL plus ZC. Then Z equal to, what is ZR, friends? The impedance of the resistor is R only. But what is the impedance of the inductor? That is JXL, that you know. What is the impedance of the capacitor? Minus JXL. Impedance of the capacitor is minus JXL. All this you know the AC analysis fundamentals. Then you have to write Z equal to R plus J into, that is XL minus XC. This is the impedance of the series RLC circuit. The impedance of the series RLC circuit equal to Z equal to R plus J into XL minus XC. What is XL here? XL equal to omega L. What is XC here? XC equal to 1 by omega C. What is omega here, friends? Omega equal to, that is angular frequency in radian per second. That is angular frequency in radian per second. Radian per second. Then you have to write omega equal to 2 pi. Omega equal to 2 pi. Where F equal to frequency, F equal to frequency in hertz or cycle per second. In hertz or cycle per second. That all of you will know. Hertz or cycle per second. Questions. If you vary the supply frequency at a particular frequency, XL becomes XC. It is called resonance condition. The frequency is called resonance frequency. That is, if supply frequency is varied, if supply frequency is varied, if supply frequency is varied at a particular frequency, at a particular frequency, at a particular frequency, XL equal to XC. At what frequency XL becomes XC? It is called resonance condition. It is called resonance condition. What are the frequency we taken? What are the frequency we are varied up to XL equal to XC? And that frequency is called, at a particular frequency XL equal to XC, and that frequency is called resonance frequency. And that frequency is called resonating frequency. Is called resonating frequency. If you vary the supply frequency, you can vary this frequency up to this XL equal to XC. Then at what frequency XL equal to XC, that frequency is called resonating frequency. Then how to calculate the resonating frequency? Therefore, at resonance condition, XL equal to XC. How to write XL equal to omega L? How to write XC equal to 1 by omega C? From this, omega square equal to 1 by LC. Then omega equal to 1 by root LC. Omega square equal to 1 by LC. That is omega equal to 1 by root LC. That is angular frequency. This is angular frequency at which condition, students? Okay, this is the angular frequency at resonating condition. Then this frequency is treated as omega naught. I'm taking this is omega naught. This at resonance condition, let omega naught, this is omega naught C, this is omega naught square. Because I have to define at resonance condition. That's why I'm taking omega. Then this is angular frequency at resonance condition. Angular frequency at resonance. Because this is I'm calculating at resonance condition. Where XL equal to XC, that condition is called resonance condition. Therefore, angular frequency at resonance condition. What is the angular frequency at resonance condition? Frequency at resonance. That is omega naught equal to 1 by root x. You can also write omega naught equal to 2 pi f naught now. That is 2 pi f naught equal to 1 by root x. From this, what is f naught equal to 1 by 2 pi root x? Therefore, what is the resonating frequency? That is a frequency at resonance condition. That is resonating frequency. The resonating frequency f naught equal to 1 by 2 pi into root x. F naught equal to 1 by 2 pi into root x. That is the resonating frequency. That is the frequency at resonance condition. Resonating frequency, or it is also called frequency at a resonance condition. So, that you have to concentrate. Yes, friends. But you know that at resonance condition, some other observations also I'm explaining here. At resonance condition, at a resonance condition, XL equal to XC, then what the impedance? Z equal to R plus J into XL minus XC. If you replate XL equal to XC, R plus J into XC minus XC, this is equal to R. That is Z equal to R. That is at resonance condition. Impedance is minimum, circuit is resistive. Z equal to R. Therefore, at resonance, impedance is minimum. Z becomes R, the remaining term is cancelled. Impedance is minimum. Impedance is minimum. And circuit is resistive. And circuit is what nature, friends? Resistive nature. Because XL equal to XC, that becomes 0. That difference becomes 0. XL equal to XC, the difference becomes 0. But don't think XL is 0, X is 0. XL is present, X is also present. XL becomes, but don't think at resonance condition, XL not equal to 0, XC not equal to 0, sir. But XL equal to XC. XL equal to XC. That is at resonance condition. Then impedance is minimum and circuit is resistive. Impedance is minimum and circuit is resistive. Then we know that this is one observation. In series RLC circuit, if you take series RLC circuit, what is I? You can write V by square root. If you write the current in this circuit, let this current is I. Let this current is I. How you can write the current in this circuit? I equal to V by square root R square plus XL minus XC whole square. This formula. Okay, that I am writing here. That is I equal to V by Z. That is R square plus XL minus XC whole square. This is the current. But at resonance condition, this is V by Z now. At resonance, Z equal to R. If Z equal to R, what is I equal to? V by R. If I equal to V by R, then what about the voltage and current, friends? That is voltage and current is minimum. Sorry, voltage and current is in phase and current is maximum. Why? This Z is minimum. Z is minimum. That is at resonance impedance is minimum. If Z is minimum, then what is the current is maximum? Current is maximum. Therefore, at resonance condition, at resonance Z equal to R, then I equal to V by R, then current is maximum. Current is maximum at resonance condition. Impedance is minimum means current is maximum. Therefore, at resonance condition, voltage and currents are in phase and operating at a unity power factor. Therefore, at resonance, voltage and currents in phase, and operating at unity power factor. Voltage and currents are in phase, and circuit is operating, at unity. Circuit is operating at unity. Operating Circuit is operating at unity. Then if you write this is voltage and this is current. Voltage and current is in phase. Voltage and current is in phase. Then what is the voltage across the inductor? You have to define the voltage across the inductor equal to I into XL. What is the voltage across the capacitor? You have to define I into XL. I into XL. Voltage across the inductor equal to I into XL, and voltage across the capacitor equal to I into XL. But you know this one, friends, XC equal to XL. That is voltage across the inductor equal to voltage across the capacitor. This one at resonance, XL equal to XC. If XL equal to XC, if you take VL equal to I into XL, replace XL equal to XC, that is I into XC. This is equal to VC. That is at resonance condition. Voltage across the inductor equal to voltage across the capacitor. Voltage across the inductor equal to voltage across the capacitor. Because XL equal to XC. I am writing I into XL, but XL equal to XC now that I am replacing. That is at resonance condition XL equal to XC. I am replacing XL by XC. Then we are getting VL equal to VC. But you know that with respect to inductor, what is the voltage across the inductor? Voltage across the inductor is leads the current. That's why this is VR. Voltage across the capacitor is lags the current. This is 90 degrees. This also 90 degrees. But these two are equal. Voltage across the inductor equal to voltage across the capacitor at resonance condition. But always with respect to inductor, current is lagging. Current is lagging means voltage is leading. With respect to capacitor, current is leading means voltage is lagging. This is the observations at a resonance condition. These are the observations. But the magnitude of VL equal to magnitude of VC. That is at resonance condition, magnitude of voltage across the inductor equal to magnitude of voltage across the capacitor. Okay, that you have to concentrate. Then I already calculated what the resonance frequency, all these. These are the some minimum fundamentals with respect to series resonance circuit. Mainly you have to concentrate at resonance condition, this one, XL equal to that I given. How to define the resonating frequency? The frequency adjusted for XL equal to XC, that frequency is called resonating frequency. Then what is the formula for? This is the angular frequency at resonance condition. This is the resonating frequency. This is the resonating frequency. Then at resonance condition, impedance is minimum. Impedance is minimum, circuit is resistive. At resonance condition, current is maximum. All these points are with respect to series resonance circuit. I equal to V by R. At resonance, voltage and currents in phase and operating. That is at resonance condition, voltage and currents are in phase, and circuit is operating at unity power. And circuit is operating at unity power. Circuit is operating at a unity power factors. That is power factor equal to unity at resonance. All these are the observations for series resonance. Then at resonance condition, magnitude of voltage across the inductor equal to magnitude of voltage across the capacitor. That you have to consider. With this knowledge, I have to draw some characteristics here. Variation of inductive and capacitive reactances with respect to frequency. How this inductive reactance and capacitive reactance is varying with respect to frequencies. Let this, I am taking the angular frequency. Let this is the omega. Take omega here. And how this reactance is changing with respect to frequency. Inductive reactance and the capacitive reactance. This positive, you take a plus XL and you take this is the minus XC. We know that capacitive reactance is negative. Capacitive reactance is negative. That's why I taken capacitive reactance is negative side. And inductive reactance is positive. That's why I taken positive side. How to write capacitive reactance? Minus XC equal to, that is minus XC equal to minus 1 by omega C. This is a capacitive reactance, minus 1 by omega C. If omega equal to 0, if you substitute omega equal to 0, if omega equal to 0, what is minus xc? That is capacitive reactance is infinity. That is, if omega is increases, then what is the capacitive reactance is reduces. That is minus xc is reduces. That is at omega equal to 0, the capacitive reactance is infinity. Yeah, this started from this. Here, this is at infinity. If omega is increases, this direction, if omega is increases, then slowly the capacitive reactance effect is reduced. Like this. Listen, sir. I'm substituting omega is infinity. Omega is 0. Omega 0 means this one. This is omega equal to 0. At omega equal to 0, this is the infinity value. This is infinity value. And if omega is increases, the capacitive reactance effect is reduced. This is which characteristics? Xc versus omega characteristics. Those are the capacitive reactance versus omega characteristics. This is minus Xc characteristics. What about XL equals, friends? XL equal to omega L. At omega equal to 0, what is XL? XL equal to 0. At omega equal to 0, XL equal to 0. Now, if omega is increases, what about XL increases? Now, here I am drawing the XL characteristics. This is the XL characteristics. These are XL characteristics. Then omega equal to 0, XL is 0. If omega is increases, what about XL? The inductive reactance is increases. XL is also clear. XL is also increases. Next, I have to draw the characteristics of net reactance. What is the net reactance? X net equal to net reactance equal to XL minus XC. This you know. Let this frequency is omega naught. This frequency is omega naught. This frequency is omega. This frequency is omega. For omega less than omega naught, omega less than omega naught, omega less than omega. This is for omega less than omega. This is for omega greater than omega. What is the observation here, sir? For omega less than omega naught, for this side, omega less than omega naught, which is dominant? Capacitive reactance is dominant. If capacitive is dominant, for omega less than omega naught, Xc greater than XL. That is, which is dominant? Capacitive reactance is dominant. That is Xc greater than XL. If Xc greater than XL, the resultant, the net for omega less than omega naught, Xc greater than. Why Xc greater than XL? This is more dominant as compared to this one. If Xc greater than XL, what is the X net? X net is negative. X net is negative. Then Xc greater than XL means that is leading power factor. This is for leading power factor. X net is negative. Now, what about at omega equal to omega naught, students? At omega equal to omega naught, XL equal to Xc, what is X net? X net equal to 0. For omega greater than omega naught, this is omega naught, then this is for omega greater than omega. For omega greater than omega naught, which is going to more dominant, inductive reactance is more, but capacitive reactance is going to decrease. Then what is the X omega greater than omega naught, friends? What is the X net equal to? For omega greater than omega naught, which is dominant? XL is dominant. XL greater than XL. What is X net, students? X net is positive. Then I am drawing the X net characteristics, net reactance characteristics. For omega less than omega naught, which is dominant? The capacitive reactance is dominant. That's why X net is negative. X net is negative. For omega greater than omega naught, X net is positive. The net reactance is positive. These are the characteristics. Clear? Omega greater than omega naught, which is greater here? XL greater than XC, this reason. Then lagging power factor, leading power factor, lagging power factor. That is in this circuit, for omega less than omega naught, capacitive is dominant, leading power factor. For omega greater than omega naught, XL greater than XC, inductive, dominant, lagging power factor. This is leading, this is lagging. What about at this one, friends? At omega equal to omega naught, at omega equal to omega naught, what is the net reactance? 0. If net reactance is 0, then Z equal to R. What power factor it is operate? Unity power factor it is. Z equal to R, then it is operating at a unity power. Clear? Any doubt? These are the variation of inductive and capacitive reactances with respect to frequency. How the inductive reactance is varying, how the capacitive reactance is varying. This indicates Xc characteristics. This indicates XL characteristics. This indicates X net. X net is 0. This is 0 at omega equal to. X net is negative. X net is positive. Omega less than omega naught, which is the dominant? Capacitive. Omega greater than omega naught, which is the dominant? Inductive. Because of inductive, lagging power factor. Because of capacitive, here leading. Like this, the inductive reactance and capacitive reactance is changing with respect to frequency. That you have to concentrate. Next, variation of I and Z with respect to frequency. Variation of I and Z with respect to frequency. We know that Z equal to square root R square plus XL minus XC whole square. The impedance equal to square root R square plus XL minus XC whole square. That is R square plus what is XL minus XC? X net square, net reactance square. For omega less than omega naught, friends. For omega less than omega naught. For omega less than omega naught, which is dominant? Xc greater than XL. Xc greater than XL. If Xc greater than XL, this one, Xc greater than XL. Negative term is more as compared to positive term. Xc greater than XL, na? This negative is more. What about the X net? Reducing. What are the X nets? Xc, that is XL minus Xc. Then Xc greater than XL, X net is reduced. If X net is reducing, what about the Z? This one. If X net is reducing, Z is also reduced. If X net is reducing, Z is reduced. If Z is reducing, what about I? Increases. That is for lower frequency, less than omega naught. If the for less than omega naught, reactance is reducing, impedance is reducing, current will increase. Current will increase. What about for omega equal to omega naught, friends? For omega equal to omega naught, XL equal to XC, XL equal to XC. If XL equal to XC, what is X net? 0. The net reactance is 0. If net reactance is 0, then what is Z equal to R? That equal to Z minimum. Then what the current I equal to? How to write the current flux? That I equal to V by R. That is the maximum. I equal to V by R. That is maximum. For omega equal to omega. At resonance frequency, current is maximum. What about for omega greater than omega? For omega greater than omega naught, which is greater? XL greater than XC. If XL greater than XC, X net increasing. If X net is increasing, what about the Z students? Increasing. What about I? Reducing. I is reducing. Now, with this knowledge, Z is increasing, I is reducing. Now, with this knowledge, you draw the characteristics. If you try to draw the characteristics for Z versus I, or Z, first I'm writing Z versus omega. Z versus omega. Let this is omega naught. This is omega naught. This is for omega less than omega naught. This is for omega greater than omega. What the observation here? For omega less than omega naught, impedance is reducing. For omega less than omega naught, friends, that is impedance is reducing. Impedance is reducing. Then you get the characteristics like this. Omega less than omega naught, impedance is reduced. Impedance is reduced. This impedance is reduced. Next, for omega greater than omega naught, impedance is increased. Impedance is reduced. At omega equal to omega naught, this Z equal to R. This omega equal to omega naught. At this point, Z equal to R. Clear? Omega greater than omega naught is XL greater than XC. What about this side? XC greater than XL. For omega greater than omega naught, it is a lagging power factor. It's a lagging power. And this side, it is a leading power. This side is a leading power. Like this, how the impedance is changing with respect to frequency. This Z equal to R. This is for omega equal to omega naught. At omega equal to omega naught. Then what is the impedance? Z equal to R. That is the minimum. Is R. Clear? Can you try here I versus omega? Can you try for I versus omega? We know that If you draw the characteristics between I versus omega, this also I already explained, omega less than omega. For omega less than omega naught, I is increases, Z is reducing, I is increases. Clear? For omega less than omega naught, I is increasing. This I is increasing. What about at omega equal to omega naught? I is maximum. At omega equal to omega naught, the current is maximum. This is maximum current. For omega greater than omega naught, for omega greater than omega naught, current is reduced. Current is reduced. This is at omega equal to omega naught, current is maximum. At omega equal to omega naught, current is maximum. These are the characteristics with respect to current under frequency. This is about what is the variation of I and Z with respect to frequency. I given the variation of XL and XC with respect to frequency. I given the variation of that is Z and I with respect to frequency. That is how to answer. Any doubt? How to discuss one more concept here. Variation of power factor angle with respect to frequency. How the power factor angle is varying with respect to frequency. Every observation you start from omega less than omega naught, omega equal to omega naught, omega greater than omega. Yes, friends. At omega less than omega naught, you know that at omega less than omega naught, xc greater than xl. That is leading power factor. If it is a leading power factor, current leads the voltage. Current leads the voltage. Current leads the voltage. Then if it is like this, current leads the voltage. This is voltage and this is the current source. If it is current leads the voltage, then angle is measured like this. Then theta is taken as positive. This is for at omega equal to omega naught. XL equal to XC. At omega equal to omega naught, XL equal to XC. If it is XL equal to XC, students, what about Z equal to? If it is XL equal to XC, what about the Z equal to? Z equal to R. Power factor is unity power factor. Z equal to R. XL equal to XC, Z equal to R. Then it is operated at unity power factor. Then finally is at omega greater than omega naught. XL greater than X. XL greater than X. XL greater than X is current lags the voltage. Current lags the voltage. If current lags the voltage, how the angle is measured? This is V. This is I. This is the. Then current lags the voltage. We are measuring in clockwise. Theta is negative. We are measuring in clockwise. That is theta is positive. That is theta is negative. Clockwise, no, theta is negative. Now, if you try to draw this phase angle with respect to frequency, if you draw this character, this is also important observation. I am drawing this character, friends. This is pi. With respect to omega, and this is plus 90 degrees. Angle is minus 9. Yes. For omega less than omega naught, what about theta? For omega less than omega naught, friends, theta is positive. For omega less than omega naught, theta is the positive. Then you get the characteristics like this. Omega less than omega naught, theta is positive. This is theta is positive. That is pi angle is positive. Omega less than omega naught, this is positive. At omega equal to omega naught, it is 0. At omega equal to omega naught, this is 0. At omega greater than omega naught, friends, angle is negative. This angle is negative. This angle is negative. This is the point omega equal to omega equal to is omega equal to omega naught pi equal to 90. We can get the variation of power factor angle with respect to frequency. That is, what is the observation here? If omega is increases, what is the observation? What is the phase angle? That is, pi is either positive or negative. If omega is increases, the phase angle is changing from positive to negative angle. Initially, this is positive angle, then it is changing to negative. It is changing from positive to negative values. That is about how the phi versus omega. These are pi versus omega characteristics. Phase angle versus frequency characteristics. This one concept. What is the variation of power factor angle with respect to frequency? What is the variation of Z and current I and Z with respect to frequency? Therefore, at resonance, Z equal to Z minimum. At resonance, Z equal to Z minimum. At resonant, I equal to I maximum. Current is maximum. At resonance, I equal to I maximum. Next, other concepts also there. How the variation of voltage across L and C as a function of frequency. Then this characteristics also that I have to explain. What are the quality factor? What are the formulas of quality factor of series RLC circuit that I have to discuss? What are the voltage across L and C at resonance condition? That also important formulas. What are the bandwidth and cutoff frequencies that also have to calculate? And these calculations also important. Then power factor at cutoff frequency relation between all these have to discuss. For time being, today I'm ending the session, students. I think one more class is there today. Please go to that. Thank you. I'm ending the session. After completing total theory only, I will solve the problems with respect to resonance. Thank you. Any doubt? Thank you.